Let us see our example here in Pulley's, the second example. Now we have this. The diagram shows a particle A of mass 0.5 kg attached at the end of a light inextensible string. I think you see. Passing over a fixed pulley. So this one is passing over a fixed pulley. This one is passing over a fixed pulley and under a light movable pulley. So this pulley is movable. B. The other end of the string is fixed as shown below. So that is fixed as shown. So that there it's fixed. What mass should be attached at B? What mass should be attached at this? For the system to be in equilibrium. So meaning, never want to take equilibrium means that there is no acceleration. So meaning, we need a mass. We don't know. Let us call it its weight, md. So let me call this md. Say, let's mass b m kgs. So I put here my m kgs, meaning it's going to be having a weight. So here the weight is going to be 0.5 g. Then this one, the weight is going to be mg with the ease. Okay, so after that, now it means that we are adding just this weight on that there. So after that, remember this one is going to be having a tension in this screen. So here we are going to be having T, then here T. Also here we are going to be having T. Now there's going to be a tension in that screen, T. Then also here, tension there. The same, because it's the same screen, that's why the tension is the same. So after doing that, now remember, at equilibrium, or in equilibrium, acceleration is equal to 0. So we start with the 0.5 kg mass. So here, it's that now, what do you mean our acceleration is going to be? Now it's that this one, our acceleration is going to be like this. But we say the acceleration, if the acceleration is here, remember, always the acceleration at the end of the string is twice the acceleration of this pulley between the two strings. So if this one is 2a, if this acceleration is 2a, then this one is going to be the acceleration here, and now it's going to be moving up like this. So this one will be a. Or this is a, this is a half a. It's up to you. Always this one is twice the acceleration here, because this one is at the end. Notice that the particle which is at the end of the string is going to be having twice the acceleration of this between the string. So that's why if here I have a, this one is going to be a. But remember, when I push this, when I pull this down, this one is going to go up. That's why the acceleration is like that. So at A, our acceleration there is in this order, 2a. But remember, our horizontal force is going to be m times the acceleration, but in the previous acceleration is 0. So R is out, and what is pushing it down is going to be now. So in simple terms, this should be equal to this. Or you say 0.5 d, then minus, is that the first pulling up is that, is equal to m 0.5 into 0, because the acceleration is 0 in equilibrium. So meaning our t is going to be 0.5 into 9.8. So our t here is going to be 4.9 newtons, a half of this. Okay, so after that, then we come to the m kilogram mass, because we need this mass to the m kilogram mass. So this now is the acceleration, and now here our acceleration is 0. Yeah, that acceleration is 0. Now when we come to this also, is that we are going in that direction up. So our acceleration in that direction, but upwards. So always RFR is equal to MA, the resultant. So what is pushing it up? We have this T and this T. So you have T plus T, then minus the M, this one which is pulling it down. So you have this T which is pulling it up, and this T, because this one is between two. So this and this. So T plus T, the other ones which is push, they are the ones which are pushing this up. Then minus mg, the weight, equal to m into 0. So that here, our 2t is going to be equal to mg. Now we have this twice this, so we have now our m. Okay, we're going to be having 2 into 4.9 equaling to m into 9.8. And so from here, our m is going to be 1 kilogram. As simple as that. Very clear. Okay, so now the mass we need to attach this for this to be in equilibrium. It's 1 kilogram mass. So this should be a 1 kilogram particle. So this is attached to here. So here I did this for Friday, but this one just is attached there. Okay, so from there now we come to part B. If B is 0.8 kilograms, what are the acceleration of the particle A and pulley B? Now, if this one, they are telling us if this one is 0.8 kg is the weight, I mean the mass. If the mass B is 0.8 kilograms, now it means that here we are going to have a weight of 0.5 times gravity, the mass. Here also we are going to have the mass times the gravity. Now, we are going to be having still the tension there, and that spin there. Which we then here we have also tension there. Of course, not the same as this because here the weight is that it's different. T, and also here T. And now here the acceleration still here is going to be in that direction at the end of the spin. So this is going to be to A, while this one, which is going to be moving up, is going to be just A. We said the acceleration at the end of the spin is twice the acceleration of this pulley between the string, between these two strings. Or say the mass between the two strings, its acceleration is twice the acceleration of the particle at the end of the string. Once you know that, the rest are very easy. Now we start with this one. The zero. This one, remember this one, they were just asking for the mass for it to be in the equilibrium. Now, here they are just telling us that now, what if this one is 0.8? Find the acceleration of this particle A. This is our particle A. Remember, this is our A. And the pulley B. So, what the acceleration of this which is A? What the acceleration of this which is twice A. So now, when I consider this 5 kg mass, now here, remember, acceleration here is like this 2A. Remember, my resultant force is equal to mass times acceleration because you say the force is in the same direction as the acceleration of the particle. The force you apply in the particle is in the same direction as the acceleration of that particle. So here is that what is pulling it down. Here we have, you see, we follow the direction of the acceleration on each. So that's what is going down. So we have now what is 0.5 g, then minus the opposite t equaling to the mass, which is 0.5 times the acceleration. Now the acceleration here is 2a, the acceleration here. So here it shall be with, okay, this is going to be 0.5 g, then minus t equaling to multiply this, we get a. I call this equation 1. Then we come to the 0.8 kg mass. What am I having here? Is that the acceleration now is up. This is going to be A. You know that my resultant force still is equal to ma. What is the resultant? Pushing it up, we have this, and this we have t plus t. They're the ones that are pulling it up, this t and this t. Then minus, this one is opposing force, 0.8 g, will be equal to the mass, which is 0.8 times the acceleration. By the acceleration in here is going to be A. So here we have 2t minus 0.8 g equal to 0.8 A. And then by the by 2, by the by 2 we have t on a 0.4 g equal to 0.4 A. This is equation 2. So we need this acceleration. What are you going to do? You're just going to add this and this. So if we add 1 plus 2, so I'll be having this, which will be 0.5 g minus 3 equal to A. Then add on this, but let us start with this. Negative 0.4 g plus t, this one will be equal to 0.4 a. We are adding because we want to eliminate this and they are having different signs. When you add this plus this, you shall get 0.1 g. This plus this, it will vanish. And this plus this, you shall get 1.4 a. And now, as you see, our a, if we multiply it by 10, we have b equal to 14. Then if we get our a here, our a is going to be 0.1 over 1.4 b. Okay, so that is going to be our acceleration. Now, the acceleration of particle A, for particle A is 2a, or you can tell me see if you multiply by 10 we have b over over 14. So our b is what? We put our b, so our a will be 9.8 over 14, which will be, when we put our b there, I'm getting 0.7 meters per second squared. So this is acceleration at B, or Pulley B, or Pulley B, because rated towards A. Then at A, we say that A, our acceleration is going to be 2 times, now the acceleration at B, 0.7, our acceleration here is going to be 1.4 meters per second squared, because we say this acceleration here is twice the acceleration there. So that's how we handle that. We are going to see more examples. I wish you well. Please don't forget to subscribe to the channel.